Welcome everyone to the last ITC lunch of the fall semester. We're entering the winter and the holidays, and our next meeting will be on the 28th of January, the beginning of the spring semester. So spring is around the corner. And we just had an excellent ITC colloquium by Anna Ijjas. And it's always a great pleasure to listen to Anna. She's such a brilliant scientist that even if the theory that she advocates has not been proven, you learn something new. It's a compliment. Our first speaker today will be Zack Slepian, who is graduating this year. And he will talk about searching for Baryon Acoustic. Actually, the title is slightly different. A new approach to the three-point correlation function of galaxies. Then we'll hear from Anna again. She's visiting us from Princeton. She spent a year here. And she will talk about how to bounce. Does that mean bouncing between places, or?
That's easier.
And then we'll hear from Sarah Wellons, sitting next to her, also a graduate student here, and she will talk about where are they now? The z=0 descendants of high redshift, massive, compact galaxies in Illustris, in simulations. And finally, we'll hear from the colloquium speaker today, Elena Gallo from Michigan, over there. So we have 3 speakers lined up, right? And she will talk about the 50,000 solar mass black hole in the dwarf galaxy RGG 118. Zach.
Okay, thank you, Avi. Can everyone hear me? Great. So as Avi said, I'm going to speak about a new approach to the three-point correlation function of galaxies. This is part of my thesis, and also some of the data I'll be showing today is actually in a paper we put on the archive that showed up yesterday. So what is the three-point function? Well, it's really simple. It's just about triangles of galaxies. You have one galaxy over here, another one over here, and another one over here. And you want to count the excess galaxies over random that inhabit particular triangle configurations. So a triangle has 3 parameters. You can use angle, side, side, that sort of thing. So here we're going to be working in terms of 2 sides, R1 and R2, and the angle enclosed by them, theta 1, 2. And so if you assume rotation invariance and translation invariance, those are all the parameters you need. And so we'll write the three-point function as this zeta of those 3 parameters. And then we're going to expand it in a multipole series where we characterize its angular dependence on cosine theta with these Legendre polynomials PL. And we just multiply them by these coefficients describing the side length dependence, the zeta sub L. So those just depend on R1 and R2. So the nice thing about this basis for the three-point function is that then you can make plots like this where you just fix the L, and that gets rid of the angular dependence, and you just plot this radial coefficient, and you can see the behavior versus 2 of the triangle sides, R1 and R2. So this is just an example of that. We'll be coming back to this plot. And the color on this plot represents the number of triangles above random with these given side lengths. And as I've said in this panel, the angle dependence is projected onto the L=1 Legendre polynomial, which is just cosine theta, so the dipole. Okay, so the 2-point correlation function of galaxies, which measures excess pairs above random, can be used for cosmology via the BAO method. So the question is, why not the 3-point correlation function? So just to remind you how the BAO method works, basically there are these 2-degree hot and cold spots on the CMB, which forms at redshift roughly 1100. And those actually come from overdensities and underdensities at that time that source slight overdensities of galaxies separated by the BAO scale today. So this is all coming from acoustic oscillations in the plasma that the universe was before the CMB formed. And basically you have this ruler in the CMB that we can measure from things like WMAP. And you also have this same scale in the actual correlation function of galaxies today. So what one does is actually takes galaxies today, measures in different redshift slices, and looks for this characteristic scale. And you can basically say, okay, I know the length of this ruler now and at different redshifts in the past, and I can normalize it by the CMB. and that allows me to measure the expansion rate of the universe in constrained dark energy. So as I've said, the BAO method in the two-point function uses a bump in the correlation function. So here we're just seeing separation on the x-axis and separation squared times the correlations on the y-axis. And this big bump is what's used for the BAO method. These are just different SDSS data releases. And basically the takeaway here is you have a bump and the error bars are getting smaller. DR11 is not even the latest. I'm going to show you stuff from DR12, although for the three-point. So the question is there a similar bump in the three-point function that can actually be used for cosmological purposes? And the answer turns out to be yes. So here, again, we're looking at the three-point function's dipole moment. So we've taken the triangles, we've projected the angle dependence onto cosine theta, and we're now just looking at how that coefficient depends on the two side lengths, R1 and R2. So these red and blue features in this plot are actually at exactly the BAO scale of 100 megaparsecs per h. And so I've boxed in solid here this red and blue feature that's due to the BAO. And basically what that means is you have a slight excess of triangles that like to have at least one side a little bit less than the BAO scale, and you have a slight decrement of triangles that have one side a little bit greater than the BAO scale. And I should mention this plot is symmetric by construction because the triangle didn't care about how we labeled it R1, R2 versus R2, R1. So that's one BAO feature. Just like in the two-point, you have this really sharp characteristic scale embedded in it. But another one I want to highlight is actually this dashed one here, where you can see there's a white kind of zero of the three-point function stretching on this diagonal from 100 to 100. So this is also actually generated by the BAO. And basically what happens here is you have a triangle where the third side, which you're not seeing on this plot, is the BAO scale, and the other two sides are actually flattened out like this, adding up to that third side of 100. So that's why the two sides you do see are lying along this diagonal where here one of them is 0 and another is 100, and here you switch and the other one's 100 and the first one's 0. And the point of highlighting this feature as well is that as you go to smaller scales, the error bars become better. So this diagonal crease, even though visually it's less strong in this plot, is actually also very helpful if you want to go do the measurement. So now let's measure the three-point function and look for this BAO feature. So that's easier said than done. The three-point function scales as n cubed, where the two-point function scales as n squared, with n the number of objects. So basically, when you count pairs, combinatorically, you just have n options for the first times n minus 1 for the second. When you count triplets, you add an extra factor of roughly n. So for 1 million galaxies, such as the number in DR12, this is not favorable. In fact, probably it's not doable in a Hubble time unless computers improve a lot faster than we think they're improving. So this would not be the way that you want to do this. So the question now is, does the multipole basis actually make this better? Is there a way to somehow work through the multipole basis that can get this faster than an n-cubed calculation? And it turns out the answer is yes. I'll just give you 2 slides to kind of show you why. Basically, we want to calculate, as I've said, these radial coefficients. One way to do that would be to sit around a particular point in the survey given by S vector, and then calculate the coefficient, and then at the end of the day, we'll average out over these S vectors. So we'll just average over all locations in the survey. And to compute this coefficient, you just need to integrate this density field given by delta against this Legendre polynomial weight that depends on the product of R1 vector and R2 vector. So here that's shown visually. You basically would sit on this red X and look at all pairs of galaxies around it, compute the relative angle between them, and then use that as your weight here and do this integral. So it looks like around each galaxy given by the red X, you need to do an order n squared operation because you have to compare every pair around it. Now there are also n red X's in the survey you have to sit on. So overall you're doing an order n cubed operation. So this is, again, the naive way to do it. That would be really computationally unfeasible. But it turns out that if you actually sit on each galaxy now given by a white X, bin the density field around it into spherical shells, and then along each shell expand the angle dependence of the density field in these spherical harmonics YLM, you can actually rebuild the Legendre polynomial that you needed without ever directly comparing pairs of galaxies. Instead, you get to just compare pairs of bins. So you would compare, say, this bin to that bin, and there would only be of order 10 or 20 bins around. There would only be of order 10 or 20 bins, period, in radius, because you choose, 10 megaparsec wide bins and go out to maybe 200 megaparsecs. So the point is, the things you have to compare has dropped enormously and now doesn't scale with the number of galaxies at all. So around each galaxy, you now have to do an order n operation because this expansion of the density field in spherical harmonics is order n, and there are still n galaxies, but now you've basically gotten down to n squared rather than n cubed scaling. So we wrote the algorithm. It's 500 times faster than a naive triplet count, and it's only 6 times slower than computing a 2-point function. And now I'll show you the results of that. But first, there's one more element we need to add. This is something called compression. Basically, when two galaxies become very close to each other, they interact strongly, so perturbation theory becomes invalid. And so we want a way to avoid getting these types of triangles in our data set. So we basically say, we'll fix one triangle side, constrain the second to be in this gray annulus, which prevents it from ever getting close to this galaxy, and also prevents this galaxy here from ever getting close to this one. And so the compression actually just integrates the second side over this gray annulus, and visually, what it does to this color plot of the radial coefficient is shown. You basically are sitting at a fixed R1 and integrating along length in R2 set by the R1. That's why this wedge gets wider. So the plots you're going to see now only have one free variable. They have the triangle side we didn't integrate over, and that triangle side is controlling the other triangle side. So this is the result of computing the compressed 3-point functions for the mean of 299 DR12 Machs. The details of those Machs are in the paper over here. These L's represent the multipole moment. And again, we're only seeing one triangle side because we've integrated out the other one. So in blue are the redshift space Mach catalogs, and in red is our perturbation theory model. So you can see the model is fitting the data well. And over here, we have this bump and this dip right around the BAO scale of 100 megaparsecs per H. So I'll quickly just show you the same thing for the data. So this data set is 800,000 roughly luminous red galaxies. They're color selected. They're from SDSS DR12, and they have roughly constant stellar mass. So you can see the error bars are a bit larger because we have a sample effectively 300 times smaller than the Machs that I showed you. But basically, the data is still fitting the model well. And you can see there's still this BAO feature over here. So I'll just skip over here to the punchline, which is that we can fit models with the BAO and models without the BAO to this data and ask what is the chi-squared penalty that the models without the BAO pay. And so for the Machs, this is the fit with the BAO, just highlighting L equals 1. This is the fit without the BAO, and you can see that without the BAO, you just can't fit the data correctly. And indeed, with the Machs, you'd get a 56 sigma detection. So that's saying if you had 300 times the volume of SDSS-DR12, you'd get 56 sigma. Now, with our data, the significance is obviously a lot more modest, but you can see that here, the no BAO model is still basically passing through this peak and trough and not fitting it very well compared to the with BAO model. So we get a 2.8 sigma preference for the BAO. So just to conclude, I've shown you briefly a fast novel algorithm to measure the multipole moments of the 3-point function. We've used it on 800,000 DR12 LRGs. The model fits well, and we have a 2.8 sigma BAO signal. And the future work that I want to do is actually analyze the full non-integrated, non-compressed 3-point function, and that should allow us to detect the BAO and use it as a cosmic distance probe, much like has already been done successfully in the 2-point function. So, thank you. Yeah, well, basically, the simplest answer to that is that the 2-point and 3-point function are independent. So think of the analogy of the CMB looking at the temperature and anisotropies versus looking at polarization. It basically gives you another independent lever, and it gives you that in the same data set. all the measurements that you need for the 3-point function are already done for the 2-point function. Now, probably the 3-point function will not achieve the precision that the 2-point function achieves, but whatever it does achieve, it will be a fairly independent measurement of the scale.
Is there a scenario where you can get new information?
Yeah, there are also degeneracies it breaks. In particular, there's a source of possible systematic error in the 2-point function that's recently been developed by several workers, and the 3-point function can actually help with that. It's also useful in breaking the degeneracy between linear biasing and sigma 8.
This is a kind of extension of that last question. Back in sort of 1980, when there was a brief flurry of interest in the 3-point correlation function, the reason that flurry of interest died out was that it was shown that the 3-point function could be expressed in a closure relation as the sum of products of the 2-point correlation function for cases where the points had been evolved by an inverse square n-body simulation, but not others. And so I guess my question, so there is a case where the 3-point correlation function might actually be independent of the 2-point correlation function, but the idea from back then was that if things evolved according to an n-body simulation, that there would always not actually be any additional information. So I guess the search for additional information might actually be interesting.
Yeah, I'm surprised by that result because certainly since the late 70s, people had been looking at these hierarchical ansatzes where they say that the 3-point function should just be a cyclic product of 2-point functions connecting each triangle side. And there is a term like that enters our modeling, but it turns out to be subdominant to the other terms that don't take that form. So certainly in the last 10 or 15 years, people have looked at the covariance of the 2-point and 3-point function, which is just the way to quantitatively ask, do they contain different information? And there is some covariance, but it should be smaller than the signal. And I think that really the way to solve that is to look at simulations and just measure both 2-point and 3-point and empirically look at what the covariance actually is. So we have all the simulations to do that. In fact, our algorithm at the same time as it measures the 3-point also computes a 2-point, so that's something we're looking at.
Yeah, I mean, we can talk about this more later, but the hierarchical model laws that were worked on in the 80s were, they were intended for small scale work, and they may have been consistent with very, very limited data sets on small scale, but it's not what you get when you develop the 3- and 4-point function in perturbation theory on large scales, or even that you get out of in-body simulation on large scale. So the information really is separated. The whole idea of being able to use the 3-point function, for example, as a test of gravitational structure formation is not a statement about the hierarchical model. It's actually a statement about the gravitational theories and perturbation theories. So you do get your information.
That's the question.
Wow, I don't think anyone has ever seen that before. Okay, well, thank you.
He knows he can find you around.
Thank you.
Okay, so thanks for the kind invitation, Avi, and also for the kind introduction. So as a cosmologist, I think one quite often gets it wrong with the theory, but one at least tries honestly. So I will be talking about today of something that most people are afraid of, namely bounces. And here I'm not meaning the bouncing from Princeton to Cambridge. That's quite easy compared to bouncing from a contracting phase, so a past universe, to a current one. But before we get to it, how to do it, we should ask, why on earth do we want to bounce? Doesn't seem to be easy. Otherwise, one would have already figured it. The reason for it is partly I already gave it in my colloquium, so it will be most of a recap. I think, and most of the people who work on bounces think that contracting phases are particularly interesting for cosmology if you want to solve the initial conditions problem, namely if you want to explain why is the universe on large scales flat and smooth, and how do you get nearly scale invariant curvature perturbations into the business which have no Gaussianity. Why is it so? Why are people interested in it? First of all, it seems like the contracting phase can smooth the universe quite easily by employing very much the same principle as one wished to use for inflation. Namely, one can use, of course, complicated version that I showed in the colloquium, but the simplest version, the ekpyrotic contraction, really just uses the fact that by adding an energy, a homogeneous energy component, the equation of state of which dominates the energy density, which is here represented by the square of the Hubble parameter h square, then this energy density can dominate for a large amount of time. We usually need 60 efforts, and this way smooth and flatten the cosmological background so that we are not surprised at the end why we have no curvature and anisotropy domination. Now, more exactly, to see this, just look at the different energy component in the Friedmann equation on the right-hand side of the equation, and you see that scaling with A, there are two that you usually have to watch out for: the curvature, which scales like 1 upon a to the square, or the anisotropy, which scales like 1 upon a to the 6, because depending on in which cosmological phase you are, one of them has to dominate. Matter, which goes like 1 upon a cube, or radiation, which goes like 1 upon a to the 4th, are not really dangerous, given that one of these two other components are there, which are usually part of the metric. So in expansion, you would be worried about the curvature because A is shrinking, but in contraction, you are worried about the anisotropy because A is growing. A is shrinking, so any kind of energy density is growing with 1 upon A, but the one that grows fastest is the anisotropy. So the prescription is add an energy density, the equation of state of which suppresses the anisotropy, and you can explain why you are flat and smooth. And because it's that simple, therefore, one should pay attention to contraction. As a result, you see that this energy density will dominate the total energy density, so one can think of this pre-phase as a phase that is dominated by the ekpyrotic energy density, or as I explained in the colloquium, the anamorphic energy density. Common to these phases is that one can accommodate the generation of nearly scale invariant superhorizon curvature modes that we also need so that we have seeds of structure, galaxies, planets, and us. And why one doesn't just say, hey, but we can all do this with inflation without having the difficulty of the bounds. Well, this I cannot explain, so I have to assert it. As I explained in the colloquium, the particular advantage of a contracting phase is that one can start with it in the dark energy phase today, and it also doesn't generate a multiverse problem. Both facts cannot be said about inflation. So if you consider these two issues a problem, then you will be particularly interested in contracting phases. If you don't consider it as a problem, you should still be interested, because this is an alternative, and we can learn, I think, different aspects of cosmology and maybe our universe from it. But contracting phase needs a transition to an expanding phase, namely what starts what we call a bank or a bounce. And this is the non-trivial part of contraction. So I don't think that we have a part with considering contraction, we have a part with considering the transition to the Big Bang, standard Big Bang expanding phase. And I will present you what really the problem is, why people are afraid of doing this. So far I was advertising for contraction or expansion or smoothing the first Friedmann equation, and everything what we need to know about the bounce or to figure what the difficulty of it is will be taught to us by the second Friedmann equation, which simply describes the evolution or time evolution of the Hubble parameter, and which again can be expressed as the negative of the sum of pressure and energy density. And through all of cosmology, we think, and this is what's given to us in Einstein gravity, mostly that this energy density is at So the minimum of this energy density is actually today, when we have cosmological constant domination. Otherwise, it should not be, so the sum of pressure and energy density not be negative, and therefore the Hubble parameter should not be positive. That means that the Hubble parameter is shrinking as long as we don't want to introduce any modifications to Einstein equations or to Einstein gravity. And this condition is called the null energy condition. Now, how does it relate to bounces? This relates to them in the following way. If I plot the Hubble parameter as a function of cosmic time, where 0 would be the time that marks the bounce, so before the bounce we have negative time, t is shrinking, so t is getting less and less negative, and if we can realize the bounce, then we reach there 0, where the Hubble parameter is 0, and then afterward, just as we are used to it, we run from 0 to positive time. Now, we also know that during contraction, A dot is negative since A is shrinking. So the Hubble parameter will be negative, and the second Friedmann equation tells us that it's shrinking, so what it really means is that if we have smoothing contraction, the Hubble parameter is becoming more negative. So one has to explain it as we approach the so-called bounce, as the scale factor is shrinking, the Hubble parameter is more negative. On the other hand, we also know that we start out at large energies, after the bang or bounce, and from there on the Hubble parameter will be positive and shrinking. So here it's becoming less positive, again according to the second Friedmann equation. So you see, the real problem is that whatever you do during the contracting phase, in order to reach the expanding phase, you have to do something that obviously either violates the second Friedmann equation because you bounce the so-called finite scale factor. The only other option is that I won't be talking about today, but other people are actually doing research on that area, is that you let the Hubble parameter go to negative infinity and come back on positive infinity. That would be a so-called non-singular bounce. So this is another area of research, but people are even more cautious there since you have to get close to the realm of quantum gravity that we are not very familiar with yet. Okay, so in my remaining few minutes, I will tell you that there is a vanilla bounce that doesn't have to violate the second Friedmann equation, can hike up to positive h, and is happening at finite value of the scale factor. What I should also mention here is just so that you watch out for it. This is a very active area of research, the question if it really is a problem that H dot becomes positive. I myself do work on it, but there has been actually a lot of work done, starting with people interested in ghost condensate theory, and also today on non-singular bounces. So it doesn't look easy, but it's not clear that it's wrong. But let's go to a case where it is not even necessary. So I have presented in a colloquium a new cosmological model when we make use of the fact that contraction can also be achieved when I introduce variation in the Planck mass or the mass of massive particles. Of course, this is a small amendment to Einstein gravity, but this is not an amendment that hasn't been done before. One example of such an amendment would be so-called scalar tensor theories. Also to mention is that in order to comply with observation, one also have to arrange, and this usually happens by hand, that the Planck mass today doesn't vary so that we don't violate solar system constraint. But the most important aspect in this context about the anamorphic contracting phase is that it calls to our attention that we should be more cautious when we amend or when we extend Einstein gravity about what we mean by contraction and expansion, which is particularly important for cosmologists. Since we don't really mean contraction, just behavior of the scale factor, we actually mean contraction, the behavior of some sort of scale factor or the cosmological background with respect to rulers, which are made out of particles. So when we talk about contraction, we don't really mean how A behaves, we actually mean, and also have to account for the fact that we measure the background evolution by ways of measuring the evolution of the scale factor. Of course, as you see, if m is constant, this is just the good old Hubble parameter. In contraction, it shrinks, and in expansion, it grows. So what we really had to achieve in it is not really that h dot or h is growing, but what's really important that this quantity, a times m, where m is again a positive massive particle, let's say a mass of an electron or whatever mass you want to wish a test mass, and this has to be growing. Now, again, it's also important to consider that the null energy condition, or energies I measured, with respect to the Planck mass. So when we talk about the null energy condition, we don't really mean that just the scale factor is shrinking, or the logarithmic derivative of the scale factor. We really mean that we are shrinking compared to, or this quantity is shrinking relative to the Planck mass. So energies are evolving relative to a Planck mass, while and this is the conventional notion why we measure background behavior relative to particle masses. And you see the conflict comes from the fact in the non-singular balances that if m and mpr both are constant, then we at the same time want to fulfill the null energy condition by claiming that the Hubble parameter is shrinking, and on the other hand, we should have it growing. So last piece of information is that this is exactly what we abandoned in the anamorphic model, as I have shown. In the colloquium, we introduced a variation of the ratio between m and m Planck, and that, and now short of time I have to assert it, makes it possible that you already see that the first condition, that the null energy condition has to be fulfilled, doesn't have to be violated by the second condition. So this simple vanilla bounds when you have anamorphic contraction can be done without violating the null energy condition, which has the advantage that one doesn't have to be worried about the usual instabilities that one is worried when one does violate the null energy condition. And just so for the outlook, of course, this model is really the simplest model what can do. In order to complete the model and make it cyclic, one has to work a bit harder, but this is work in progress. Thank you. Yeah. Yeah. Yeah, I think it's a very good question. So there are two ways of, if you recall the other picture, sorry, just because it's easier, there are two ways of generating a bounce, and this is, one is exactly as you mentioned, that was the way when one lets the Hubble parameter become really infinitely negative. That would mean that one collapses the scale factor to 0 or below the Planck line and come back on the other side. These are the so-called, what you mentioned, singular bounces that really would require knowledge of quantum gravity. There is also another area of research where one doesn't do this trick. Exactly for the reason that you mentioned, one says, okay, we really don't know enough of quantum gravity or about quantum gravity to make a controlled statement about how this happens. So let's add some new kind of stress energy to the right-hand side of the Einstein equation that would stop the contraction or stop this behavior that h dot goes to 0. This is the usual way in Einstein gravity, and that would raise the scale factor. That would mean you bounce at the finite scale factor completely in the classical regime, and the only thing that you really have to be worried about, which is a non-trivial question, is these instabilities. And this is within Einstein gravity, and I was talking about how you can amend this.
That implies that the mass Planck will change in time. Have you explored that possibility?
So my model exactly relies on the fact that the Planck mass is a time varying, but it's also, so that was the idea of the model, yes, but the time variation, so it settles into just as the universe after the bounce settles in a vacuum, this field also have no time variation anymore. So during standard Big Bang evolution, the Planck mass should not evolve in any case, neither in my model nor ever.
So does this help with the problem of the low entropy initial conditions, also the past hypothesis type things? Because it looks like if you draw a line diagonally there, you get some symmetry between the blue and the yellow curves, kind of like different branches of hyperbola. So maybe overall, is there a restored time symmetry?
Okay, so this is a very good question. So in principle, it's a big problem. And then I won't be able to give a complete answer, because here's the issue. We think that we know what's the issue with entropy when we remain in the realm of Einstein gravity or don't violate the null energy condition. it's not yet clear what are the rules of the second law of thermodynamics. Even generalized second laws of thermodynamics, for example, by Aaron Wall and collaborators, have only been explored by assuming the validity of Einstein gravity to a long scale. And there is no unique answer to the fact what's happening with entropy. One has to explore it. However, my answer for this would be that this bounce probably doesn't help you with the problem, but you really have to look at the entire cosmological scenario and see if you can complete it to be a cyclic scenario. That means that you have cycles of bounces. Then you can talk more meaningfully if you can solve the entropy problem or not. So I don't think that this particular construction will teach us much about that.
The good thing about the cyclic model is that anyone who doesn't believe it will eventually be convinced of this. Thank you very much. Thank you.
Great. Can everyone hear me? Yes. All right. All right, so I'm going to be talking about compact elliptical galaxies, which are a type of galaxy that we see commonly in the high redshift universe, but can be difficult to find in the local universe. So here are some distributions of observational sizes of galaxies with binned into different stellar masses going up and down, and at different redshift bins going left and right. And it's further broken down into star-forming galaxies in blue and quiescent galaxies in red in each panel. Now, if we look around redshift 2, around 10 to the 11 solar masses, we can see that there's a big difference in the typical size of a star-forming versus a quiescent galaxy. And the quiescent galaxies have very small sizes of just 1 or 2 kiloparsecs. These are some examples of what these galaxies look like. And we can see that if we look at the peak of this histogram and we trace it forward to low redshift, there's a very strong evolution in the typical size of a quiescent galaxy with time. And so the question that I'm going to be addressing in this talk is, what happens to these galaxies over here? Where should we expect to look for them in the local universe, and what might prompt this strong dependence on the typical size of a galaxy with time? Now, I'm addressing this question in the context of Illustris, which doesn't need a lot of introduction with this crowd, but this is the cosmological simulation that we have in Lars's group. It's a periodic volume of about 100 megaparsecs on a side, which is initialized in the very early universe and evolved forward to the present day, with dark matter and baryons co-evolving throughout the entire volume. So there are tens of thousands of galaxies forming and evolving and interacting situated within a cosmological context. And so I can just dig through it and look for the galaxies that I'm interested in. And we do find some of these galaxies. If we go to redshift 2, we find galaxies like this on the left. These are mock observations of galaxies from the Illustris simulation. And on the right are the analogous HST observations of real compact elliptical galaxies. So having seen galaxies like this in the simulation, we have some confidence that if we find out how these evolve, it might tell us something about how these evolve in the real universe. To quantify this a little bit, what I mean when I say compact is that I go to the size-mass plane, this is at redshift 2, and draw a line here for constant sigma 1.5. This is sort of a surface density criterion. It's similar to what the observers use. And I pick all the galaxies of a few times 10 to the 11 solar masses, which are more compact than this line, and trace them forward 100 billion years down to redshift 0 to uncover where they are in the local universe today. And to give away the punchline, the answer to the question, what do these galaxies turn into, is that they turn into everything. There's a wide dispersion in the stellar masses that these galaxies end up with at redshift 0, with some galaxies having gained almost no stellar mass, and some having gained almost an order of magnitude of stellar mass. So where does this come from? Here I've sorted all the galaxies' descendants by their relative change in stellar mass, so the factor by which their mass changed between redshift 2 and redshift 0. Here are the guys that changed by factors of 10. Most of them are closer to factors of a few, with some few having actually lost mass in the intervening 10 billion years. This is a blow up of the same thing down here. And we can sort out this change in stellar mass into a few different components. The dominant source of the change in stellar mass is from ex situ stars, which are stars that are formed in other galaxies and brought in through mergers. These two panels look almost identical in most cases, with some little differences at the low mass end. And so for the vast majority of these galaxies, this is driving almost the entire change in stellar mass. These panels now are on the same scale as the inset, and so you can see that there's up to about a 20% change in stellar mass from in situ star formation, a little loss from stars evolving off the main sequence, and in some cases a significant amount of mass loss through stripping. But ex situ mass is really what is driving this evolution. Now here are some images of what these galaxies look like at redshift 0. I've ordered them by the mass of the descendant, and I'm using sort of a funny color bar here, which is two-dimensional, where light to dark shows you the stellar surface density, and blue to red shows you where the stars from the compact progenitor lie within that descendant. So the color tells you the fraction of the stars along the line of sight which were present in that original redshift 2 compact progenitor. And so there's a gradient from red to blue here, just because these are the least massive descendants, so they're composed almost entirely of the same stars, whereas these guys are composed almost entirely of other stars. And you can see some interesting morphologies. Most notably that in many cases there's a gradient in color going from red on the inside to blue on the outside. And in some cases up here it's hard to see where the compact galaxy is actually. So how did they get this way? I'm going to show you a few examples here. This is a time sequence of one individual galaxy evolving from redshift 2 over here to 0 over here. And we can see that this galaxy is more or less minding its own business, falls into the gravity well of a much more massive galaxy, and gets completely disrupted and consumed in this merger. So its identity is effectively erased from the galaxy population. The reverse can also happen, of course. The compact galaxy itself can disrupt other galaxies in mergers and accrete its stellar contents onto the outskirts and build up an envelope of ex situ particles, so that you end up as the core of your more massive descendant, which is the source of this gradient in color. You can also have mergers which are very equal, both in mass and binding energy, so that the two galaxies really thoroughly mix their star particles together and you get a uniformly green appearance at the end of the day. And of course, there are some galaxies which just sit around and nothing happens to them, which is boring to look at but interesting to think about. So how can we break this down a little bit quantitatively? How common are these types of evolutionary pathways? Well, one way to sort these out is to look at the cumulative stellar mass profiles. So this is the stellar mass enclosed at a given radius. There are two lines here for each of these examples. The black line, which includes all of the stars interior to a given radius, and the red line, which includes only the stars from the compact progenitor. And if you look at the ratio of the red to black line at an inner and outer radius, that ratio tells you what type of descendant it is. So here the ratio is 1 at all radii, here it's large at all radii, sort of middling at all radii, and here it's 1 at low radii and higher at larger radii. And so we can sort these galaxies into these descendant types. And when I do so, I get a distribution that looks like this, where about half of the galaxies are this core type, about a third of them were more or less undisturbed, and a few of them were mixed or consumed in mergers. And those of you with sharp eyes will notice that there is not always a one-to-one correspondence between the number that you see here and the number of points you can count. This is because two compact galaxies can have the same descendant at redshift 0. In fact, the only way we got such an equal merger in this case is that two compact galaxies merged together. And the environment that a galaxy has at redshift 2 does have some determining power for what type of evolutionary track it will take. So here now I'm showing you the change in mass between redshift 2 and 0 against the change in size, where I've just colored the points according to what type of descendant they have. And now if I instead take the same x and y axes but just change the color of the points, to indicate the number of mergers that the galaxy has undergone in that time, with red being very few mergers and blue being more mergers. You can see a gradient where the galaxies that gained very little mass had very few mergers. And if I recolor this again, according to some environmental parameter, so this is the distance to the fifth nearest neighbor at redshift 2, where blue is dense environment and red is isolated, we can see that the galaxies which don't change very much preferentially live in very sparse environments at redshift 2. The notable exception being these two galaxies here, which are marked as triangles because they happen to be satellite galaxies at redshift 0. So if we want to look for these galaxies in the local universe, we should be looking in places where they're protected from mergers, either in isolation or as satellites and clusters where the orbital velocities make it difficult to merge. All right, so in summary, I've looked through Illustris for a sample of these massive compact galaxies at high redshift, found ones that are reasonable analogs to the observed galaxies, and traced them forward to redshift 0. Found that the dominant source of mass growth is ex situ mass acquired in mergers, which can gain you from no stellar mass to a factor of 10 in stellar mass. And that if we want to look for these galaxies in the local universe, we should either be looking deep into the heart of the most massive galaxies today, or in regions where these galaxies can be protected from mergers. Thanks. Yep.
So of the most massive galaxies in Illustris at redshift 0, maybe half were of this type. How did the other half form?
Well, so notably, half of the ones, you were looking at the plots that I was showing just now, right? Half the ones had a compact progenitor at exactly redshift 2. Many of them had a compact progenitor at some other time, and I just didn't catch them when I looked exactly at redshift 2. There is a trend where the more massive you are at redshift 0, the more likely you are to have had a compact progenitor at some point along the way. Thanks, Abby.
Okay, hi everyone. So I'll try to keep it on time. I'm going to switch gear a little bit and present a purely observational work. I hope you won't mind. So in reality, this work was led not by myself, but by my grad student Vivienne Baldassari at the University of Michigan. And it's part of an ongoing collaboration with Amy Rines at NOAO and Jenny Green at Princeton. So the title already gives you the punchline. That is, we have recently discovered a 50,000 solar mass black hole in the nucleus of a relatively nearby dwarf galaxy named RGG 118, and I'll explain where this comes from. So what is the relevance of this discovery before I walk you through the actual observational work? So you're all aware of the known scaling relations between massive black holes sitting at the center of galaxies and broad properties of their hosts on scales that greatly exceed the black hole sphere of influence. So the scaling relations, i.e. the black hole mass to stellar velocity dispersion or black hole mass to bulge mass, point towards a tight interplay, some sort of feedback whereby the growth of the black hole somehow regulates the growth of its host galaxy. So there is very little doubt that all massive galaxies, and when I say massive, I say in excess of a star or so, host supermassive black hole in their nuclei. It is not that obvious that the little galaxies, so with masses, stellar masses well below 10 to the 10 or even 10 to the 9 solar masses, do so. And if they do, it is not clear whether those black holes sit on the extrapolation of those empirical scaling relations at the low mass end. Now, this is not purely interesting from a phenomenological perspective, but also whether or not dwarf galaxies host black holes at their center can give us some handle, somewhat counterintuitively, on the very mechanism, the predominant mechanism, by which black holes were seeded in their host galaxies at very high redshift. So I will talk actually more extensively about this topic in the talk later today. But here is just to give you a sense of what I'm referring to. This is theoretical work by Voluntary and Natarajan, and it's in two realization of cosmological evolution of galaxies at the nuclear black hole seeds. You are seeing the expected evolution of the so-called M sigma, so black hole to stellar velocity dispersion relation at by redshift 1, for the case where the black holes were seeded from essentially the evolution and death of massive stars on the left-hand side, versus a scenario where the black hole seeds were extremely massive, so coming from the global collapse, for instance, of a massive gas cloud at high redshift. So you're seeing that the way sort of this population of low mass, low velocity dispersion objects is approaching the local scaling relation, local by redshift 1, is different in the sense that you can create, sort of approach the relation from the top versus the bottom and create a plume, a scatter, either above or below the relationship. And there are also other interesting predictions as far as the occupation fraction, the black hole occupation fraction of black holes varies by redshift 0 in these two different scenarios, and I'll talk more about that later. The point is, though, it is unfortunately difficult to find, detect, measure the presence of black hole in dwarf galaxies. So to give you a sense for why that is, for a 10 to the 5 solar mass black hole, the sphere of influence is only resolvable out to a distance of 1 megaparsecs. So essentially what we need to rely on for this type of investigation is to look for signs of accretion-powered emission from these black holes. And so when I refer to AGN activity, I'm talking about Eddington ratios in the range of either Eddington limited or 10% of it. So pioneering work in this sense has been led by Jenny Green and Louise Ho, starting about 10 years ago. And more recently, Amy Rines and others have started to push the threshold for this investigation to dwarf galaxies with masses, with stellar masses below essentially the Large Magellanic Cloud, so log M star lower than 9.5. So what you're seeing here is the result of this recent work by Amy Rines, where she mined the NASA Sloan Atlas for a signature of AGN activity coming from, as identified by narrow and broad lines, so narrow line ratios in the standard diagnostic diagrams, or broad H alpha emission indicative of motion due to essentially black hole gravity. And so out of a sample of about 25,000 galaxies, she isolated a sample of about 200 candidate AGN in nearby dwarf galaxies. So what I'm going to report on is now essentially follow-up spectroscopy that we undertook with the Magellan telescope of one particular object. We have a larger campaign that Vivienne is working on at the moment, but this one was a particularly neat example in that the estimated mass for this black hole is to date sort of the record holder, the teeniest supermassive black holes discovered. So this is the object, RGG 118. This comes from the Rhines, Green, and Jiha catalog. So it's a neat dwarf galaxy at a distance of about 100 megaparsecs. This is the Sloan image shown there. And here on the bottom, you're seeing a series of the standard narrow line emission ratios, which are commonly used to identify and separate out AGN versus star formation triggered photoionization signatures and objects that are somewhat in the middle. So the two data points refer to the same object as measured in the Sloan and then Magellan spectrum. So why do we need follow-up spectroscopy? Well, the reason is fairly straightforward, because we are pushing this investigation to luminosity and potential black hole mass ranges where the signature, the virialized motion from the gas that would give you broad H-alpha or H-beta emission, leads to features that are of the order of 7, 8, 900 kilometers per second. So in other words, we are starting to compete with stellar properties in terms of the amount of gravity, the amount of motion that broad feature reveals. So we need to make sure to go back at later epochs and look for events, signature of broad features that are non-transient in nature. The first obvious hypothesis being supernovae, but it could also be Wolf-Rayet stars or things like that. So you already know what the answer is for this object. Indeed, we went back, acquired a high-resolution spectrum with a Magellan MAGE instrument, measured a narrow complex, and on top of which, or below which actually sits a broad H-alpha feature indicated in the cyan model there. So after careful modeling of this complex, the full Wheatal maximum of this feature is estimated to be near to 800 kilometers per second. And along with its luminosities, you can use the so-called single epoch reverberation mapping relations to back out a black hole mass of 50,000 solar masses. Of course, there is quite a large error in this measurement, as it relies on a series of scaling relations between, most importantly, the luminosity in this line and the size of the broad line region as inferred by Caspi and collaborators, that kind of work. Strong evidence for an AGN in this system also comes from Chandra. So we were awarded directed discretionary time later last year and found a grand total of 6 photons in the nucleus of this system, which is enough to measure a luminosity well in excess of the Eddington limit for 10 solar masses. So again, from the accretion power emission of this black hole, we are essentially we are looking at the system as sort of a mini or micro quasar, if you will. Its bolometric Eddington ratio is of the order of 10% or so, given the black hole mass. The last piece of information I wanted to give you is about where this system lives compared to the local scale relations. So you're seeing here, we were able here to measure the gas velocity dispersion, which in turn scales with the stellar. And you can see that RGG 118 sits on the extrapolation of M sigma at the low mass end. It is quite a bit of an outlier with respect to the bulge black hole mass relation, which is not particularly different from other dwarf galaxies that are known to host massive black holes. And its SDSS spectrum suggests the presence, or is consistent with the presence of a pseudo-bulge, even though we have approved cycle 23 HST multi-band imaging that will enable a much more accurate decomposition of the host galaxy. So I'll stop here. Thank you. So, in principle, yes. However, I've spent a great deal of work over my career to estimate what the probability for contamination from X-ray binaries is. And so given the luminosity function of both high and low mass X-ray binaries and the distance of this to the system, you can estimate the probability, which happens to be very low. But I'll talk about this in detail later today, kids. So I think per se, you cannot obviously rule out to court that this is a very bright X-ray binary, but the two pieces of evidence combined, I think, argue for a massive black hole.
Just assume it's a gradient at the editing unit. Does that let you go backwards to the mass? What is that mass?
If they were at the Eddington limit, 10 to the 30. So if you're talking about correction of a factor of 10, that's very high. So after that, it would be like 4 of the order of 40 to 38.
Okay, so is that to say that even if it were a gradient at the max, it's possibly a lower limit?
Yeah.
Yeah, no, when you said 12.3 x error bar, does that mean cube root of 10 is like a factor of 2 where maybe between 25,000 and 100,000? Sorry, I just wasn't sure I was reaching that.
Hi.
That's very nice. Do you remember, have you seen the work from a couple of years ago by my student Susmita Chakraborty?
Yeah, sure.
Yes, so she did this thing on the lower mass end when you could see it. But of course we took 2,000 kilometers a second as a cutoff for a broad binary. So this of course is consistent with that. So the spectrum is probably as hard as you would expect from simple distance.
Yeah.
Most likely. So it's in that range anyway, but it could be interesting constraints.
Yeah, I'm not.